Hello everyone, I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the property of hysteresis in magnetic materials. So before understanding hysteresis, we should know about the domain theory. So we'll discuss first about the domain theory and then go for understanding the hysteresis. So what is this domain theory? It is also known as Weis theory of magnetism, after the name of the scientist Weis. So it is called as domain theory or Weis theory of ferromagnetism. So according to this scientist Weis, ferromagnetic material consists of a large number of regions called domains. They are very small in size, of the order of 10 power minus 6. And they are spontaneously magnetized. So when we say spontaneously magnetized means even in the absence of a magnetic field, these domains are spontaneously magnetized. Means whenever I take a small region, all the dipoles in that region will be oriented in a particular direction. So if you see in the diagram here, this is a ferromagnetic material we have taken. This is the ferromagnetic material and these are domains. This is domain 1, domain 2, domain 3, domain 4 and domain 5. So it is just a diagrammatical representation. There may be many number of domains, but here for example we have taken 5 domains. So when you consider each domain, you see all the dipoles are oriented in a particular direction, in the same direction inside the domain. And if you see in the second domain also, all of them are oriented in the same direction. Like that, as a domain if you take, all the dipoles are oriented in the same direction. That is what we have to understand about the orientation of domains. Now this spontaneous magnetization, when we are talking, it is due to the parallel alignment of magnetic dipoles in each domain. So this parallel alignment of the dipoles in each domain is responsible for spontaneous magnetization even when no electric or magnetic field is applied. So here we are not applying any magnetic field, but still the domains, all the dipoles in a given domain are oriented in the same direction, that gives rise to spontaneous magnetization. Now, different domains possess different orientations and hence the net magnetization is 0. Now, when we are considering the material as a whole, it consists of a number of domains and each domain as a result will have a particular direction and the net magnetic moment due to all the domains may be 0. But when an external field is applied, there are 2 possible ways of the alignment of domains. So what happens to these domains when an external magnetic field is applied? So 2 possibilities. The first one is there may be motion of the domain walls. So whatever domains we have seen now, these domain walls may move. Or there may be rotation of the domain walls may rotate. So these 2 possibilities may be there whenever we are placing it in an external field. Now these domains arise due to minimize the energy of the material so that the total internal energy will be minimum. This domain theory also helps us to understand how the total energy, internal energy can be maintained minimum. Now, the domain walls which are parallel to the direction of the applied field will grow in size. Means whenever we are talking about application of an external field, what happens to the domain walls? There may be motion or there may be rotation. So in case of motion, what happens here? They may grow in size than the other domains, and that we are calling it as motion of the domain walls. Also, the other domains which are opposite to the field direction are reduced. Means one is growing in size and the other is reducing in size. So we may say that there is motion. So I will try to understand very clearly with the help of this figure, this concept. Now, the first one, if you see here, these are the domains. We have taken domains like this. 1, 2, 3, 4. And if you see the magnetic moments, so as a whole, this has a magnetic moment in this direction, the domain as a whole. There means all the dipoles here are oriented in the same direction. That is why the resultant here is in this direction. And here the resultant is upward. Third, the resultant is like this, and here it is like this. This is in the absence of a magnetic field. H is equal to 0. In the absence, they are having spontaneous magnetization, but the net magnetic moment is 0. So, domain orientation in the absence of magnetic field. Now, we are applying a magnetic field. We are placing this material in a magnetic field like this. The magnetic field is like this. Now, what happens? Domain enhancement and shrinkage due to weak fields. So, domain enhancement means those domains which are in the same direction, they will grow in size. You see here they have grown. This is how the domain size has increased for this one. And the other domains, they are decreasing in size. This is increasing and this is shrinkage we call. So, the domain size will vary. And the third one we can see domain rotation due to strong fields. When the applied field is very strong, now what will happen? These also will start rotating like this. There will be a slight rotation. And due to saturation and very high fields, what happens? They are oriented in the same direction. Rotation as well as motion. So this is what we need to understand about domain theory. So as the magnetic field is strong, the domains can rotate in the field direction, and that is called as rotation of domain walls. So motion we have understood, and now this is the rotation in the presence of a strong magnetic field. Now coming to hysteresis. What is hysteresis? It means lagging of magnetization B behind the applied magnetic field. So we have seen the concept B is proportional to H. Means whenever we are placing a material, a ferromagnetic material in a magnetic field, then magnetism is induced in it. And the induced magnetism is denoted by B. So if this B is lagging behind H, then we call it as hysteresis. Means they are not in phase with each other. They are lagging behind. So why they are lagging behind is the energy that is supplied to the specimen during the magnetization is not fully used. So whatever energy we are supplying to magnetize the specimen, it is not fully used. Some of it is lost. So the balance of energy left in the material is produced in the form of heat. And this loss of heat, we are calling it as hysteresis loss. So hysteresis means lagging of the magnetization when compared with the applied field. And this loss of energy during the process of hysteresis, we are calling it as hysteresis loss. And this phenomenon of magnetic hysteresis is irreversible. You cannot reverse it. Okay, and this is a characteristic of the ferromagnetic material. And the loop or the area refers to the hysteresis loop. So we are going to understand this loop. Means when we are plotting a graph for H versus B, we said H and B are lagging behind. B is lagging behind H. Means when we are magnetizing a material, when we withdraw, so you may get a loop like this. So this loop, we call it as hysteresis loop. And hysteresis loss occurs below the Curie temperature. So whenever it is behaving like a ferromagnetic material, this hysteresis loss occurs. Now let us fully understand the entire phenomenon here, or how hysteresis is occurring in this magnetic material. Now what we do is we take an unmagnetized specimen of a ferromagnetic material and we subject it to increasing and decreasing magnetic field. First we try to increase the magnetic field or we decrease the magnetic field. And magnetic field B, that is induced, varies as a function of H along a closed loop. So whenever we are trying to trace it, the variation in magnetic induction with the variation in magnetic field intensity, we get a closed loop, and that loop we are calling as the hysteresis loop. So take an unmagnetized ferromagnetic material and subject it to a magnetic field. So as the magnetic field increases, how the magnetic induction increases, and when the magnetic field is withdrawn, how it decreases. When we are tracing it, we get a loop, and that loop we are calling it as hysteresis loop. Now let us see the curve that begins at the origin O. So we are starting from this point O. So what is this point O? We are taking the field intensity H along the x-axis. H is taken along the positive x-axis, and along the negative x-axis we are taking minus H, means the applied field. And along the y-axis we have taken B, the magnetic induction, and along the negative axis it will be minus B. So this will be the origin O. Starting point, we take it as the origin O. Now from this point, if H is increased, as H is increased, the field B begins to increase slowly. And how this field increases? Because of the displacement of the domain walls. So we have discussed in the Wies theory or the domain theory. So as the applied field increases, slowly there will be motion and then rotation of the domain walls. So as the domain walls start moving, so the magnetic induction also increases. So how we are tracing it from O? It is first increasing slowly and then it increases more rapidly and finally attains a saturation value and becoming independent of H. So when we are increasing the value of H, the value of B first increases slowly and then rapidly, and then it reaches a saturation point. This is the saturation. So what do we understand by saturation here is it becomes a constant. Means even if you vary the value of H, there will be no further increase in B. That is why we say it is independent of H. It becomes a saturation. And this value of B is maximum and is the saturation flux density. And that corresponds to saturation magnetization, MS. So when the magnetization is reaching the saturation point, then we call it as MS. And why it reaches the maximum or saturation is all the domains by this time have been oriented in the direction of the applied field, and there are no more domains left to get oriented. So even if we apply more and more magnetic field or increase the strength of the applied field, the magnetic induction will not increase. It has already reached the saturation point. So we call it as saturation magnetization. And this value of saturation magnetization, we are denoting it by BS. BS denotes the saturation. So once it has reached the saturation, then what happens here is we are trying to decrease the value of H. We are trying to withdraw the applied field. Whatever field we have applied now, we are trying to withdraw the applied field. That is, trying to decrease the strength of the applied magnetic field. Then what happens? B also decreases. As H increases, B increases. So when H decreases, B also decreases. But it follows a path AC instead of the original path AO. What is the original path when we were increasing the field? It was going like this from O to A. Now when we are decreasing the intensity of the magnetic field, it should have come from A to O like this only. But it is not happening like that. What happens here is, it is following a different path. While withdrawing or decreasing the magnetic field, it is coming along AC. This is the path it takes from A to C. That means what we understand here is, B is lagging behind H. B is behind H. Why it is behind H? Because at this point, if you see, the value of H is 0. At this point, H is 0. So ideally, if it has come back from this along the same path, B also would be 0 and then there is no lag. But here, it has come along a different path and it has reached the point C when H is 0. Means, when H is 0, B is not 0. It is having a particular value which we call it as BR. So H becomes 0, but B does not become 0. It is having a value equal to OC, which we denoted by BR, because the domains does not return back to the original position. So when we have seen in the domain theory, on application of the magnetic field, these domains start orienting in the same direction as that of the applied field. But now when we are withdrawing the magnetic field, all the domains will not come back to their original position. So still they will take some time to come back. So that is why there is still some magnetism left in the material. So that is why the flux density remaining in the material, we call it as residual magnetism. The magnetism that is still left in the material, because all the domains have not acquired their original position. So we call it as residual magnetism, and we denote it by BR. BR here denotes the B suffix R denotes the residual magnetism. Now what it indicates? That the material remains magnetized even in the absence of the applied field H. So the applied field H is 0. There is no applied field, but still it is having some magnetism BR. So what we call this is retentivity or remanence. The power of retaining the magnetism, we call it as retentivity or reminiscence of the material. Now, this retentivity of a material is a measure of the magnetic flux density that is remaining in the material, even when the magnetic field is removed. Now, if the magnetic field H is now increased in the reverse direction, now we are going in the reverse direction, means we are trying to withdraw the magnetic field, we have reached a point O, the origin, where H is equal to 0. But at this point, still there is some residual magnetism denoted by BR. Now, to make this BR, what we do is, we apply the magnetic field in the reverse direction. This is in the opposite direction or the negative direction. So, applying the field in the reverse direction, what happens? The value of B decreases along the path CD. What is the path it takes? From C to D. Definitely when we are increasing it in the negative direction, this goes on decreasing, and at a particular value of the applied magnetic field, that is negative, we will have B to be equal to 0. So at this position, B becomes 0. So this particular value of H, where the magnetic induction becomes 0, we are calling it as Hc or minus Hc. So it becomes 0 when H attains a value of OD. So this is OD, O to D. So it means to reduce the magnetic induction inside the material to 0, a field of magnitude Hc must be externally applied. So in order to bring it to 0, what we did, we are applying a magnetic field in the opposite direction. Means opposite to the direction of the original field. And this Hc is called coercivity or coercive force. So at whatever value of the applied field, the magnetic induction becomes 0. We call it as a coercive force or coercivity. And this coercivity, it is a measure of the magnetic field strength that is required to destroy the residual magnetism inside the material. Means at this particular point, what is happening? B is becoming 0. How it is becoming 0? By applying the reverse magnetic field. So this field strength which destroys the residual magnetism, we are calling it as coercivity. And if the applied field is increased further in the negative direction, means even after B becomes 0, all the residual magnetism is destroyed. We try to increase the magnetic field further. What happens here is the saturation is reached again. It will go along the direction DE. It is reached in the reverse direction from D to E. So as the value of H increases, so this value B increases in the negative direction, means minus B. So on reversing the variation of the field, a curve similar to ACDE is traced through the points EFGA. So what happened here? Even after becoming 0, B becomes 0, we have increased the field in the negative direction. So we have reached the saturation point. Thus we call it as minus Bs in the negative direction. Now if you are further increasing, now we again start increasing the field. Then what happens? We will reach a point minus Br. What is minus Br? That is, even when the applied field becomes 0, still there is some residual magnetism, but in the opposite direction. That is why we are calling it as minus Br. And at points C and F, where the specimen is magnetized in the absence of any external field, it is said to become a permanent magnet. Means at this point O, there is no magnetic field, still there is some residual magnetism at this point C. And also in the reverse direction at the point F, the applied magnetic field is 0, but still there is some residual magnetism in the opposite direction. So at these 2 points C and F, this material is supposed to be acquiring the magnetism which is permanent. Now if you continue further increasing the magnetic field, so it will trace, the curve is traced like this along EFGA. EFGA. So this closed curve, what is the closed curve we are seeing? We have started from A and we have come like this, A, C, D, then to E, F, G, and again to A. So this is giving a complete loop. So this represents a cycle of magnetization. This is a complete cycle of magnetization, and this is the hysteresis loop. And this loop we are calling it as the hysteresis loop. Now this loop helps us to calculate the hysteresis loss, the loss in magnetizing the specimen. So to understand more about hysteresis, You can refer to this book Electricity, Magnetism and Electronics by Dr. S.L. Gupta. And for all the other terms, you can also refer to Introduction to Dynamics by David G. Griffiths and Concepts of Physics by H.C. Verma. Thank you and see you again.
Like, share and subscribe. Hit the bell icon for more updates.